Okay, so in this video, we're going to be talking about limits, and that is the most fundamental concept in calculus. The reason why I came up with this lesson is because all of calculus is based off of the idea of limits. We have two areas in calculus. We have derivatives and we have integration. Derivatives has to do with finding gradient, and integration has to do with finding area. So this is area, this is gradient at a single point, and this is area underneath a curve. So limits are very, very important when it comes to calculus. So that's why I want to give a very basic low-level introduction to what a limit is. But I'm going to be doing this in terms of gradients and not in terms of area. Right, so basically the area, if we want to calculate gradient of any function, so if we're given a function and it's a straight line function, and if I want to find the gradient, which is represented by the letter M with the bar on top, so if I want to find the gradient, my gradient is going to be equals to what they call the rise over run, where I take some point here, which is some 2 points on this graph, and this will be some point X and Y, and this will be some point X and Y, right? So these two being points X and Y, so we can call this Y2 and Y1, and this is X2 and X1. So what we can say if we want to find the gradient for this particular shape is that we say Y2 minus Y1 over X2 minus X1. So basically we're finding the change in Y over the change in X, in the X values. So the change in the Y values over the change in the X values. And if I'm to say that this first point here, and I call the first point, let's say 2 and 3, and I call this point 1 and 1, right? So this point is 2 and 3, and this point here is 1 and 1. Basically, if I want to find, okay, so yeah, if I want to find the gradient here, I'll come and then I'll say that, so the Y value is Y2 is 3 minus Y1 is 1 over 2 minus 1. And this will be equal to 3 minus 2 is 2, 2 minus 1 is 1, so my gradient happens to be 2. So my my gradient happens to be 2. Now, this here is a very simple problem. If you want to find the gradient of a straight line, all the lines on this straight line up to infinity will give us the gradient of 2. However, what happens when we have much more different types of situation? Let's say, for example, I have a graph, and this graph is curving, and I want to find the gradient of this particular graph. And let's say, for example, I pick this point and I pick that point. If I draw a line that's passing through these 2 points, right, you can see that the shape, the gradient of this line will be different from the gradient of, let's say, for example, if I want to find the line between these 2 points here, or I could say these 2 points here. If I draw a line between these 2 points, it's going to be a different graph, or it's going to be a different line. The gradient of this line is not the gradient of this line. So what I'm trying to say is that here, this method of using rise over run, y over x, the change in y over the change in x, will not work for all types of graphs, because some graphs might also come looking with the shape like this. Some graphs will come with many different shapes, and we cannot use rise over run everywhere here. So what we can do is that we can derive an equation that will help us to find the gradient between any 2 points here. So let me go on a clean page and then start with the graph. And I say, let's look again at the straight line graph that I had at the beginning. So I'm just going to make this a little bit bigger. And I'm going to say that I'm taking this point and I'm taking that point. Now, this graph is a graph of y. So y is equals to x, for example. So basically what this means is that the value of y depends on whatever x is, right? So if x is equals to 2, then y is equals to 2, right? But we can have many different functions. We can have y is equals to x plus 1, right? And then if we want to find the value of y, we say that y is equals to whatever, let's say x is equals to 5, then we say 5 plus 1. Then when x is equals to 5, we can say that y is equals to 6, right? So basically, but another way to write y, we can say that f of x, this is just a way to say that y is a function of x. So we say that to get the value of the function, we have to input here some value of x. So it will be actually better if we actually think about this in terms of f of x. And so what I can say is that here I have f of x because this was y and this is just x, right? So this point here, if I want to name this point, this will be point x, right? And whatever I'm going to input in this part x here, so whatever value I'm going to input in x, right, is what I'm going to put there. But in this case, because we don't know yet, I'm just going to put f of x. The reason why I'm saying that is because if I want to find what y is when x is 5, then I say that f of 5. And if when f is 6, then I say f of 6. When f is 7, then I say f of 7, right? So if I want to find the value of y when f is 6, I write it like this. That's the notation. So now looking at this particular case, that's why I'm saying that the input at this particular point where x is, we don't know what x is, so we're just going to call it x. The input will be x. And then when we look at this second point here, now this point is to the right of x. So we can say that this is x plus some particular value. If this was 5, this would be 5 plus some number I don't know about, 5 plus some x, right? So this could be 5 plus 1, and this would be 6. If this was 5 plus 2, then this would be 7, and the list goes on. So what I'm trying to say is that if this is x, if this here is x, this is x plus some value to the right. I'm just going to call this value h, right? So this particular point here is x plus h, while this is x. H is the distance. H is the distance between these 2 points, between x and x plus h. That's h. So now if I want to name this point here, this point would be x plus h, because this is what we have here. The value of this point is x plus h. If h was 5, if h was equals to 1 and x was equals to 3, then this would be this x plus h would be equals to 3 plus 1. So this would give us, so basically this would give us a 4. That's what we'll put here, but we don't know what x plus h is equals to, so with that we just put it as it is. And then for f of x, we know that the input that we're putting in is the value of x at that point. At this point, the value of x was just x, but at this point, the value of x is x plus h. So I'm gonna write here x plus h. So that is my two coordinates. The first coordinate, this is the first coordinate, and this is the second coordinate. So I'm just gonna write here that my x1 is equals to x, my x2 is equals to x plus h, and then for here I'm going to say that my y value, my y1 is equals to f of x, and my y2 is equals to f of x plus h. So then that means if I want to find the difference, between these 2 points, if I want to find the gradient between these 2 points, my m, I'm going to have to say that my m in this particular case, my gradient is the difference in y value. So that's y2 minus y1 over x2 minus x1. Okay, so I'm running out of space here. Let me just clear some space. Just move this to the right and then move that to the right. So here we're saying that my gradient is equals to my y2 happens to be f of x plus h minus f of x, which is my y1, over x plus h minus x, right, which is my x2 minus x1. And here at the bottom I can see that x will subtract with x, so I'll be left with this is equals to f of x plus h minus f of x, all this is over h. So this becomes the gradient for this particular graph here. Now, when it comes to graphs that look like this particular graph here, when it comes to these particular shapes, it's very hard to get the gradient between 2 points that are very far apart. What we usually care about is we want to know what is the gradient at every single point. We want to know what is the gradient at a single point, at this point, at that point, at that point. We want to know individual gradients. We want to know what is the rate of change of these particular points at every single point. The idea of calculus and limits then is born to say we want to find out something called the instantaneous rate of change. Now, when you hear the words instantaneous rate of change, it's kind of a bit, it's kind of a bit absurd, because how can you call something instant and you say that it changes? If something is rate of change, we're looking at 2 points. But if we're looking at instantaneous rate of change, we're looking at something that is happening in a single point in time. Take, for example, a car. I'm not gonna. Okay, my artwork is really not the best. So if we're looking at this car and it has wheels, if we want to calculate the speed of this car at every single point, we can look at the wheel of a car. This is one way to do it. And the wheel of a car, we want to know the distance traveled at this point, or from this point to this point. I don't want to pick points that are further apart, like to pick that point and this point. I want to pick points that are so close to each other that I can know the speed at every single millisecond of the car, right? So the way we can do that is, like I said, we pick 2 points that are very close to each other. We pick some point x1 and some point x2, but these two must be very close to each other such that the distance between them is close to 0. So what can I do? Let's say, for example, I want to know between 3 seconds and 4 seconds. The difference between these 2 seconds happens to be 1. But I think we can get it smaller than that. If I want to get the speed per millisecond, how about if we take the distance traveled from 3 seconds all the way to 3.0001 seconds. But I think I can actually get this value closer and closer, the difference between these two closer and closer to 0, because the answer that I'm going to get here is going to be negative 0.001. 01. But I think I can actually I can actually add more zeros here and get this answer closer and closer to 0, because when we round off this answer, we are going to round it off, and if we round it off to 2 decimal places, this is going to be just 0.00, of which is just basically 0, negative 00. So what if we say that 3 seconds minus 3.0000000? What if I were to add an infinite number of zeros here? The point that I'm trying to make is that the difference between these two times frames, or these two x values, is supposed to get closer and closer to 0. We are supposed to limit this value for it to get as close as possible to 0, right? So what I'm saying here is that when I look from x to x plus h being the distance between x and x plus h, I'm trying to get h as close as possible to 0, so that I can so that it seems as if I'm looking at one particular point, even though I'm looking at 2 points that are really next to each other. That's the idea of a limit, right? So I'm going to say that in this equation here that we just happen to have calculated, this equation here happens to be the equation of a limit. Now, what am I saying? I'm saying that if we want to find the limit, I say that h must approach 0, and the equation that we use is f of x plus h minus f of x. All this is over h. Now that we have derived the equation of a limit, so this is the limiting expression, this is the limiting formula, and what I wanted to point out is I want you to get it in your head that this equation here is talking about gradient, because we found it when we were trying to find the gradient of between 2 points. Now, because of that, let me use this equation here to give an example. Let's say, for example, f of x. Let me write it at the bottom. Let me say f of x is equals to x squared, right? And I want to use this here to derive a gradient formula for this graph. What I do is that I say f of x is equals to x squared. And f of x plus h, remember we spoke about this, we said whatever goes in here is what we will substitute in the place of x. So this means that this is x plus h squared. X plus h squared, we can expand the bracket to get x plus h and x plus h. This is equals to x squared plus 2xh plus h squared. So then when we come here, so this is x plus h. When we come here, we're going to say the limit as h approaches 0 of f of x plus h. Then we substitute, it's x squared plus 2xh plus h squared minus f of x. F of x is x squared. All this is over h. Now I want you to notice that this x squared will cancel with this minus x squared. So what I'm going to be left with is limit as h approaches 0. And I'm going to be left with 2xh plus h squared over h. This is going to be equal to, now I'm sure you can see that we can actually factor out h on top, so we can take out h, and then this will be left with 2x plus h over h, and then this h will cancel. So what I'll be left with is 2x plus h. But remember what we said by, if I'm left here with 2x plus h, remember what I said about h. H is a value that is so small that it's close to 0. It's 0. As the value of h is approaching 0, as the difference between these 2 points is getting smaller and smaller, that it looks like 0, that's what h is. So h can just fall away because it's 0 anyways. If I take your weight of, let's say for example, you weigh 20 kgs, and I give you a feather that weighs 0.00001 kilograms, this is not going to add any effect to this. If I make you stand on a scale and you weigh 20 kgs and I let you hold a feather of this size, it's not going to change your weight. It's going to be negligible. Same as this value of h. So what I'm saying is the h falls away and the answer that I'm left with is 2x. That is my gradient formula for this particular function. I'm going to make out another video where I'm going to be dealing with more and more examples of limits, but this was just a basic introduction to limits. And this is limits with derivatives. Now there's other things that we need to look at about limits, and I'm going to make it in a later video. But right now I want to focus on using this formula here to solve problems that are involving with limits. So that's it for this video. Thanks for watching.